In this lecture, we're going to look at graphical probabilistic models. I'm going to give a brief overview in general on these kinds of models, Bayesian networks and Markov random fields, illustrating some examples of application in bioinformatics. But we're going to focus mostly on hidden Markov models because these are very important in bioinformatics, especially in sequence analysis. So let's start with the idea of representing probability relations between variables with graphical models. This is a very convenient way of representing these relations, dependencies and independencies of different variables. In the case of Bayesian networks, we create directed acyclic graphs. That is, there are directions in the edges joining the different variables, and these represent which variables are conditionally dependent on which other variables. In Markov random fields, we don't use directed connections, we use undirected graphs. And we use these graphs to represent which groups of variables are dependent on each other and can be conditionally independent from the rest if some values are known. Then we're going to look briefly at dynamic Bayesian networks because hidden Markov models are an example of creating a Bayesian network where we can imagine a sequence of events or sequence of changes as if it were occurring through time. It doesn't actually need to occur through time. It can be stepping across a large sequence, for example, a sequence of DNA, proteins, or something like that. But there is this notion of order. We have things that are in the past and things that come in the future. So let's start with Bayesian networks. The idea here is to represent the joint probability distribution of a set of random variables, in this case A, B, and C, by representing how they are dependent on each other. So what we are indicating here is that the joint probability distribution of these random variables can be written in this way. The probability of C given A and B, C is dependent on A and B, and then the probability of B given A, B depends on A, and finally the probability of A, which does not depend on anything else. And this is indicated by these arrows here. Of course, we can create different factorizations of the relations between these variables. We can write in different ways, but these Bayesian networks, the indication of these conditional dependencies can allow us to express things like causal relations. For example, we can say that the grass is wet if it rained or if somebody turned on the sprinklers to water the grass. So both of these cause the grass to become wet. However, if it rains, then generally people will not turn on the sprinklers because there is no need for that since the grass is already watered. So we can represent that in this way, in which the probability of turning on the sprinklers depends on whether or not it rained, and the probability of the grass being wet depends on whether or not somebody turned on the sprinklers and whether or not it rained. Rain is something here that is independent from everything else. Sometimes it rains, sometimes it doesn't, but that probability does not depend on whether somebody turned on the sprinklers or what happened to the grass and so on. So we can use a Bayesian network to specify our knowledge about the relations between the different variables. And what we have here, the graph, is this representation where we have the different variables, their connections, and so on. The nodes in the graph represent the different variables. Each node represents a variable. We have these arcs, these edges connecting the nodes, which are directed to represent conditional dependency. So this arrow here means that C is conditionally dependent on B, but B is not dependent on C. And we can have this notion of parents and offspring. So the offspring are the variables that are dependent on the parents. You see here A and B both influence C. C is dependent on A and B. So these we can imagine as being the parents of C in this graph. We can also indicate in the graph, sometimes if you see these graphs, you can see an indication of whether or not a variable is observed, and this will be a shaded node in the graph. And we can also indicate parameters. So parameters typically are not considered to be random variables, but they may affect the distributions that we are estimating for random variables. So if you want to include parameters in the Bayesian network, you can also use this notation. But the idea here is that once we specify how the variables are related, we can write the joint probability distribution of all the variables by looking at the conditional dependencies here. And the idea is that the joint probability distribution is the product of all the probabilities of each variable conditioned on the joint probability of the parent. So, for example, here we have the probability of x1, x2, and x3 not conditioned on anything, because x1, x2, and x3 do not have any variables on which they are conditioned. But for example, x4 depends on x1, x2, and x3. So if we were to create some tables with probabilities or something like that to represent this in a particular instance where x4 could have a set number of values. For example, suppose that x4 could be 0 or 1 with some probability, then the probability of being 0 or 1 would depend on the combination of values of x1, x2, and x3. And this is what is indicated here on these arrows. And the same thing for these other variables, x5, x7, x6. A different way of representing relations between random variables is to use Markov random fields. In this case, our graph is undirected. We do not have arrows pointing from one variable to another. We just have edges connecting the different variables. And so we have a certain number of nodes, which are the variables, and arcs, the edges connecting them. What we are trying to represent here is that two variables will be conditionally independent given everything else if it blocks the connection between the two. So in general, if we observe or fix the values of a set of variables that block all the paths between group V and group U, then the variables in U and V become independent from each other. So this would be the idea here. If we observe the values in group C, now once these are fixed, nothing that happens in B will affect A, because any information that could come from one variable to the other would go through C, and C is fixed, so nothing can pass through there if we imagine it that way. And this is what we are representing here. So basically we are saying that these variables here on this side will become independent from the variables here if these are known or observed or fixed, their values are fixed. We can represent conditional independence in this way by looking at these groups, and an important group in the graph for this is the clique. A clique is a set of nodes that have connections between all pairs in the set. And a maximal clique is a set of nodes that is a clique and to which we cannot add any new node and still remain a clique. So let's look at this graph here. We can see maximal cliques here. For example, this 2 and 1 would be a clique because 2 and 1 are connected to each other. But it would not be a maximal clique because we could add 5 and still remain a clique, since 5, 1, and 2 are all connected to each other. So this is an example of a maximal clique. Then we have 4, 3 here, we have 6, 4, 3, 2, and so on. But note, for example, that 4, 5, 2, 3, this square here, is not a clique because there are no connections between 4 and 2 or between 3 and 5. If we had all these connections, this would be a clique, but in this case, it's not. Now, this is important because once we have these maximal clicks, and because of this property of the conditional independence between the groups, we can write the probability distribution of all the variables that we have in the Markov random field by considering only the products of the joint distributions of the variables in each maximal click. So if we could write this by considering only the combinations of these three, then these two, and so on, instead of all the combinations at once. This can be particularly useful if we have some more structured architecture in the Markov random field, and there are some variants like restricted Boltzmann machines and so on that can make learning the parameters of these distributions much easier. But basically we can have this some function here of the combinations of values that can be, this sometimes is called a potential function, and as long as it's normalized, we have some normalization constant, which basically is the sum of all the values of these functions for all the clicks, so that the multiplication over all the combinations of values in the variables adds up to 1. That's necessary for this to be a probability. But we can have these functions here as a function of the combinations of values, and then given some data from where we can measure the frequencies of combinations of values, we can adjust the parameters of those functions, and so we can actually have models with parameters that we can train and then give us an idea of how the variables, the probabilities are distributed, and we can use the architecture of this graph to express some knowledge that we can have of the relations between the variables. So an important difference here between these two is the way they represent these conditional dependencies or conditional independencies. In the case of Bayesian networks, we have these directed edges that specify, for example, here that C is dependent on A and B, but A and B are not dependent on C. This is a unidirectional dependency. So this allows us to express some dependencies that Markov random fields cannot represent. On the other hand, Bayesian networks cannot have loops. They are acyclical, and Markov random fields can express these dependencies between sets of variables where we are not specifying that one is dependent on the other, but basically the group of variables is dependent of each variable dependent of the others. So there are different things that we can express in the relations between the variables, but the general idea is that we can use these graphs to express some knowledge that we have about how the variables influence each other. To give some examples of applications of graphical probabilistic models in bioinformatics, we have, for instance, this is a paper about the inference of networks of genes, so the interaction between genes from microarray data. One example here, using Markov random fields to find evolutionary constraints on the residues, amino acid residues at the surface of proteins at the interface where the proteins contact. So in this case, we can write a Markov random field connecting those residues that are spatially close to each other, and then looking at the data, we can check the parameters for functions that express the combinations that we find in these residues. So in this way we can see if there was a deviation from simply a random distribution, and how evolution is constraining the combinations of residues at those places. So also for homology detection and structural alignment in proteins, gene regulation, so on. Basically, these probabilistic models allow us to use large sets of data where the relations may be very complex and hard to specify with rigid rules, but where we can find these relations, statistical relations between the different variables. But one particularly interesting graphical model is these dynamic Bayesian networks, where we are using these relations, these dependency relations, to express something that is happening in sequence. We can imagine it happening over time in step 1, step 2, and so on, but we don't have to be limited to time. It can be when we are following, for example, along a protein sequence or a DNA sequence. So time here is a more or less abstract concept, just indicating that there is this order. And a Markov process is a stochastic process where the state at each step, at each instance, depends only on the state on the previous step. So this happens a lot, for example, in some board games where you throw the dice, like in Monopoly, for example. You throw the dice and then you move your piece on the board, and the probability of falling into a given place at each play depends only on the place you start when you roll the dice, so where you finished on the previous play. And we can represent this in a Bayesian network by indicating that each variable, so the state at each time, is only dependent on the state at the previous time. So x2 is dependent on x1, x3 is dependent on x2, and so on. And we can compute the joint probability distribution of all of these states as simply considering the probability of the first state. There is some random choice here with some distribution, and then multiplying all the transition probabilities between the states as we go along the sequence. Okay, so this is just a simple Markov process where we have this chain of events depending only on the previous state. But a hidden Markov model is a bit more complex, where we have this Markov chain of hidden variables. We cannot directly observe what happens there. This is the hidden part. But then we have emissions of something that we can observe that depend on the state that we are at each instant. So the probability of some emission here, y, and these are the observed variables, depends on the state that the hidden Markov or this Markov chain here of hidden variables is at each instant. So basically we need, we can represent this in this way, where x1, x2, x3 represents the state at each time step. Or sometimes you can see this representation. Note here the notation is different. This x1, x2, and x3 represent different states. And what we have here is the probability of going from this state to that state, from state 2 to state 3, and the probabilities of emitting each observable value in each of these states. So typically, the convention is that the matrix that gives us the probability of changing from one state to the other is called A, and the matrix that gives us the probability of emitting each observable symbol here as a function of the state is called B. Now at this point this is a bit abstract, but I will give some examples of how we can use this. But what we need to specify the hidden Markov models, the parameters that we have, is if we have n states, then we need an n by n matrix with the probabilities of transitioning from any of the states at time t to any other state at time t at the previous time. So basically this is the previous state, and this is the current state here, and the probability of being in state j at time t depends on what state we were at times t minus 1. So we are assuming that the probability of the state at time t depends only on the previous state. And this is represented here by this Markov chain where each state depends only on the previous one. So if we have n states, we need an n by n matrix to specify all of these probabilities. Note that this is not really n by n independent values, because since these are probabilities, the rows and columns must add up to 1. So there is some values here are dependent on the others, but we need this matrix to specify the probabilities of transitioning from one state to the next. And then we also need this part here. We need to know the probability of emitting each of the possible symbols depending on the state that we are in which we are at that particular time. So if we have k possible symbols that we are emitting, the observable values here, and if we have n states, we need a k times n matrix that gives us the probability of emitting some particular symbol if we are in this particular state. So for each of the k symbols, we need to consider also each of the n states that we can be in. Again, these are probabilities, so they are not all completely independent, but we need these values to specify the probabilities of emitting any particular symbol from any particular state. And finally, since we need to start the Markov chain here, we need a probability distribution for the first state in which we are going to start. So basically, we are going to need n probabilities that indicate for the first time step which state we will have. Of course, these are not completely independent. If we specify n minus 1 values, the remainder must be whatever is left for it to add up to 1, because this is a probability. But we have these n probabilities specifying the probability of the first state in the Markov chain. Okay, so why do we need this? We have this Markov chain with hidden values. We have these observable emissions from the Markov chain. Let me give you first just an example. This is a bit old by this time, but it's an example where it's easy to understand how we can use hidden Markov models to model some aspects in bioinformatics. So this is a use of hidden Markov models to predict gene structures, the different parts of the gene, intergenic regions, promoters, exons, introns, and so on. So basically, the hidden states are these. This is the diagram, the state diagram of the hidden Markov model, where we have the intergenic region, and then we have things like introns, exons, we have the untranslated 5 terminal regions, and the poly-A regions, and things like that. So these are the hidden states, because when we are looking at the sequence of DNA, we don't know, we cannot observe directly whether we are at an intron, an exon, an intergenic region, something like that. So these are the hidden states in the hidden Markov model. And they have probabilities of transitioning from one state to another. For example, the first intron can step into the first exon, and then the second exon can go to an intron again. There are different types of introns and exons here. We have this intergenic region that can go to this side, the 5' side of the gene, and then when it goes back to the 3' side, it will end up again at an intergenic region, and so on. So all these errors are values in this n by n matrix specifying the probability of transition between the hidden states. And now we also have probabilities at each of these hidden states of emitting those observable symbols. And in this case, the observable symbols are the actual basis of the sequence in the DNA, so the actual nucleotide symbols that we know from the sequence. And now, using that information, given a large number of sequences to train the model, and we're going to see how that can be done. Once we have all of these probabilities here, we can, given a sequence, determine what are the most likely states that we have, the hidden states, so we can map from an observed sequence to a series of states here that we can use to indicate where in our sequence are we looking at an intron, an exon, an intergenic region, and so on. So this is one possible application of hidden Markov models, but actually there are lots of applications of hidden Markov models in bioinformatics, such as grouping similar sequences. PFAM is organized by using hidden Markov models to represent different families of sequences. We can use this for sequence alignment and search. Hummer uses hidden Markov models for sequence comparison in multiple sequence alignment and in sequence search. This was an example here for gene prediction, for aligning phylogenetic trees, structural alignment of RNA and things like that. So there are lots of applications in bioinformatics. Basically, whenever we are dealing with sequential data, we can use hidden Markov models most of the time. But it's also used outside bioinformatics, basically for temporal patterns, for recognizing temporal patterns when we have this progression, this sequence of events. And this can be used for voice recognition, for even in wireless communication. There are hidden Markov models are used for, or at least the Viterbi algorithm for minimizing the error rate in transmissions in Wi-Fi and so forth. So this is a general approach to sequential information, sequential patterns, but it's widely used in bioinformatics because we deal a lot with sequences in bioinformatics. Okay, so let's see what we can do with hidden Markov models. Let's suppose that we have our model established, already trained. We have all the parameters we need. So we have the matrix A with the probabilities of transitions between states, the matrix B with the probabilities of emissions from each state to an observable variable, and the vector pi, which tells us the probability of starting the Markov chain at each particular state. Now, one thing that we can compute is the belief state at time t, given all the observations up to time t. So this is the joint probability of having that particular state at time t and all the observations that we saw before according to the model as we have defined here. Now, this is computing all the possible combinations of states up to time t would be prohibitive because we have an exponential growth in the combinations. But since the state at times t only depends on the state on times t minus 1, and the probability of emission at any time t depends only on the state at that time, we can compute this probability here at time t using this forward algorithm. So basically this is again that idea that we have from dynamic programming, where we can take advantage of previous calculations and simplify the number of computations that we need to do. So what we have here is the belief state for the time t, so the probability of having this particular state at time t can be computed by the probability of the emission of what we observed at time t, assuming that we are in that state, and then multiplied by the transition probability from the previous state to the current one, and the belief in that previous state summed for all the possible previous states. So we are summing here for whatever may have happened at time t minus 1. We are using the belief, this probability at times t minus 1. This is the same that we are computing here. And we are also considering the probability of transition from that previous state to the current state where we are now. Now we can doing this, we can compute easily the probability of being at some particular state at times t, just looking at the probabilities for all the different states at times t minus 1. What we need is when we go back all the way to the beginning, we also need this for time t equals to 1, so the first step. And this will depend on the emission of the first symbol in our sequence. Remember that these y's are what we observe, so we have all the sequence of observations up to time t, and the pi value, the probability of the Markov chain starting with that particular state. So one thing that we can do in bioinformatics with this is, if we have a hidden Markov model trained to represent a family of sequences, so we have the matrices and the pi vector computed for that family of sequences, given a new sequence that may or not belong to that family, we can compute the probability of that sequence that we observe here being generated by that hidden Markov model. So basically, we compute the belief states at the end of the sequence. We take the maximum one, and we know what is the probability of that sequence being generated by the hidden Markov model. And this allows us to assign our sequence to a family of sequences, even when the sequences are very different and we cannot use alignment algorithms, because we cannot really match the residues from one sequence to the other, but we can use the hidden Markov model to represent some sequential structure along all of this sequence by these probabilities, and so create these groups of these families of sequences that are more powerful, in a way that is more powerful than just by aligning and comparing the actual sequences position by position. Another thing that we can do is, if we know all the parameters of the hidden Markov model, we can compute the most likely sequence of hidden states. So given the sequence of observable emissions, these y values, we want to know what is the most probable sequence of hidden states. Now, this is a dynamic programming algorithm. We have two matrices. They have n by t cells, where n is the number of possible states and t is the number of times the time steps, so the size of the sequence that we have here. And in one of these matrices, let's call it matrix 1, we have at each position in the matrix the maximum probability of the state of that particular at that particular position. So we are taking the maximum from the previous column, using both the emission probabilities, taking into account the symbol at that time and the transitions between the previous states. But we are looking at each column at the probability of the most likely path, a sequence of states to reach there. So basically, we are multiplying from the beginning at each step, multiplying the previous the probability of the path at the previous step and the transitions and emission probabilities. On the other matrix, we simply retain the state corresponding to this maximum probability here. So this is something that is similar to what we do in sequence alignment, where we compute these matrices. The difference here is that we are not comparing two sequences, but we are going along the time. So our in the vertical, in the different rows, we have our different states, but in the columns, we have our time steps. But at the end, since we know the state corresponding to the maximum probability in the path so far and the maximum probability for that particular position, we can then trace back from the end of the matrix and going through all of these previous states until we reach the beginning. And this will give us the path, the sequence of hidden states that is most likely given this sequence of observable variables. This can be used for things like speech synthesis and recognition, in solving the problem of correcting errors in wireless communications, because we can imagine that the hidden states are the actual message and the observable states are the values that we are measuring, but that can be affected by some error. And in bioinformatics, we can use this, for example, to predict the differences between coding and non-coding regions of sequences. This is something like we saw previously in that gene scan algorithm that used the hidden Markov model to model the different states, the different hidden states that represent what each part of the DNA sequence is doing in the organism. So we can, by looking at the most likely sequence of hidden states, we can map what each part of the sequence is doing in the, for example, in regulation, expressing proteins, introns, things like that. Now, it's one thing. Sometimes it's easy to confuse the forward algorithm and the Viterbi algorithm, but they are not the same thing. The forward algorithm is giving us the probability of that particular sequence of observations and some final state. So basically, we can use this to estimate the likelihood that this particular hidden Markov model can generate a given sequence of observations, but this is not telling us what the sequence of hidden states is. It's just giving us the probability of obtaining this sequence of observations. And the Viterbi algorithm is actually giving us the most likely sequence of hidden states that we can have given the set, that sequence of observations. So these are two different ways in which we can use the hidden Markov model if we have all the parameters. So note that we are assuming that we have the matrix with all the transition probabilities, the matrix with all the emission probabilities, and the vector with the initial probabilities at the starting step of the Markov chain. But we need to compute those parameters based on data. So suppose that you have a family of sequences and you want to train a hidden Markov model that represents this family of sequences. In order to do that, we need to compute these parameters, these matrices and this vector. So to do this, we will see another example of the expectation maximization approach. This is the Baum-Welch algorithm for training hidden Markov models. And what we do is we start with an initial guess for all of these parameters. So A is the matrix of transitions between different states, consecutive states. B is the matrix with the probabilities of emitting the observables, depending on the state. And pi is the vector with the probabilities for the initial state in the Markov chain. And we have these two passes, the forward pass and the backward pass, that we are going to use to compute these probabilities. In the forward pass, this is basically the forward algorithm. We are computing the joint probability of each state at times t and all the observations from the beginning up to time t. Note that this depends on the parameters that we initially guessed. So we are using all of these parameters to compute these probabilities, and we saw this in the forward algorithm. Basically, we start at times 1 with each state using the pi value, so the probability of starting at that state, and multiplied by the probability of emitting the value that we observed at the beginning of the sequence if we are at that particular state. And then we compute forward for each time step by going to the probability of being in each particular state at times t minus 1, considering the emission so far, multiplied by the probability of transition between this state and the state I at times t, and also taking into account the emission for the symbol at times t. So this is the forward algorithm, and it allows us to compute for each step in the process the probability of each of the possible states given all the observations, the joint probability of each possible state and all the observations up to that time t. Now, the backwards pass allows us to compute a different thing, which is the probability of all future emissions starting from this point at times t, assuming that we have one particular state I at times t. So if at time t we have state I, what is the probability of encountering all the observations we have from times t plus 1 to the end of the sequence? And this can be computed backwards by starting from 1 at the end and then looking at the emission probability at the next step, so at times t plus 1, and the transition between states from times t plus 1 to time t, and the emission probability there. So we are using this beta at the forward position at times t plus 1, and then computing backwards for each times t. But note that these are two different things. This is the joint probability of being in this particular state at time t and having all of those observed emissions up to times t. And this is the probability of the future emissions, assuming that we are in this particular state at times t. Now, with these two, we can create this, estimate this likelihood function, and this is the expectation step in the expectation maximization approach. So remember that we need to have a likelihood function so that we can optimize our parameters by maximizing the likelihood. But in order to write that likelihood function, we need to compute the probabilities of the data, assuming the parameters, and in this case, what we can observe, which is the observed sequence. And so we need these probabilities here that we compute in the forward pass and the backwards pass. So basically, the probability of being at state I at times t, given all the sequence that we observed and assuming this initial guess for the parameters, for the matrix A, B, and for the vector pi, is the product of these two. So we can see here, remember that in the hidden Markov model, in the sequence of states, each state only depends on the past, and the emissions only depend on the current state. So what we're doing here is we are considering the probability of being at state state I, and having all the things that we observed up to times t, multiplied by the probability of everything that we will observe up to the end of the sequence, from times t to the end of the sequence, assuming that we are at state I. So this is the alpha and the beta multiplied here, where the alpha is the probability of this state at times t and everything we observed so far, and beta is the probability of what we're going to observe after times t, assuming that we are in this state. So the probability of being in this state at times t, considering all the sequence, is the fraction of this divided by all the possible states that we can have at times t. So this would be the probability of being in state I at times t, and now we can compute this for all the different states at time t. Another thing that we need is also the transition between the two. So the probability of being in state I at times t and at state j at times t plus 1. So in this case, we are considering the probabilities, this probability of being in state I at times t and having observed all the sequence so far, which is what the alpha is giving us. Then we are considering the probability of all the emissions after we jump to state t plus 1, and everything that will be emitted, observed in the future until the end of the sequence. This is what the beta gives us. And this A here is the probability of transition between this state I and the state J, and this is the probability of emitting the next symbol. So we are considering in the alpha everything observed so far, but here we are considering the emission of the next symbol at times t plus 1. And again, we now divide this by the sum of these values for all the possible combinations of states at times t and times t plus 1. And basically we have this gamma, which gives us the probability of being at some particular state, given all the sequence of values. And this C here is the probability of the transition between the states, given the observed sequence of values, and also always assuming our previous guess of the parameters. Okay, so this now gives us the likelihood function, because this is something that gives us the probabilities as a function of the parameters. Remember that the parameters all come here when we are computing these alphas and these betas and these expressions here. So now we can move on to the maximization step, where we update all of the parameters, pi, a, and b, in order to maximize the likelihood. That is, to maximize the probability of the data and all of those states. Okay, so this, I'm not going to detail the expressions here, but basically we are computing the derivative equaling to 0 for the maximum, and what we get here is that the pi will be given the best estimate for the new values of this vector, which is the probability for the starting state on the Markov chain, will be given by these gammas at the beginning. So this expression here, the probability of being in this particular state at times 1, considering all the sequence that we have, this will be the best estimate for the starting probability for the Markov sequence. The fraction of each transition, so basically we are in A trying to estimate the probability of transitioning between state I and state J. We are going to look here at all these probabilities that we computed between state I and state J along time, and we're going to sum them over time and normalize this by the marginal probability of each state over time too. So basically we are recomputing the probabilities of changing from one state to the other by summing this over the whole sequence of time steps that we have. And then for B, which is the probability of emitting each symbol, we do the same thing, but now we're going to consider only those cases where we actually have this symbol emitted, and we're going to integrate this over time and again normalize by the probability of being at each particular state. So in short, what we have here is we are going to use a previous estimate of the parameters to create these expressions that give us the probabilities as a function of the parameters, and now we are going to use that to optimize the values of the parameters by maximizing those probabilities. That is, we are going to compute the maximum likelihood value for all these parameters. So to sum up, we start with the forwards and backwards algorithm. So first we start with an initial guess for the parameters. The forwards and backwards algorithms give us respectively the joint probability of each state and all the observed emissions so far in the forward algorithm, and the conditional probability of the future emissions, assuming this particular state at each time. This is what the backwards algorithm gives us. With this, we can compute the probability of the hidden state at each time, given all the observed emissions in the sequence, and also the joint probabilities of consecutive transitions, of consecutive states between one time and the next, given all the observed emissions that we have. So with this, we can now create this the likelihood function that we can maximize by adjusting the parameters to better values, which will then lead us to different values here when computing the likelihood function, and so on. So we are going to go backwards and forwards here, as we saw before, using the expectation maximization approach, and until we converge, or until enough steps pass that we consider the model to be trained. This does not guarantee that we can find the optimum solution. It may overfit because we have lots of parameters, and if we don't have enough data, it can find some trick to model the training data well, and then it doesn't generalize. So it depends on the conditions and the data that we have, but it generally works, and it has all these practical applications in sequence analysis in bioinformatics. Also, hidden Markov models are generative models, because since we have these probabilities, we can set the model running and use them to create new examples, new sequences of observables by playing through all of these probabilities. So basically, we roll the dice and we use those probabilities to generate new examples. We can use them to classify, for example, either by computing the sequences, or by computing the probability of some sequence being generated by the hidden Markov model. In this case, if we have different hidden Markov models representing different groups, by computing these probabilities, we can assign a new sequence to one of the groups. This is done in PFAM, for example, for organizing protein families. Outside bioinformatics is done for speech recognition and things like that. So to sum up, we saw graphical models, Bayesian networks, and random Markov fields. These are two different ways of representing relations between variables, and these are useful for in bioinformatics often when we have to deal with large amounts of data, noisy data, and we want to capture these relations between many different variables using probabilities. So these graphical models allow us to express what kind of relations we are allowing, what basically our previous knowledge, for example, limiting the relations between the residues that are spatially close together, or limiting which kinds of genes can affect other kinds of genes, and so on. And by creating these graphs, we can input some information and specify which variables are related and how they are related before we move on to actually computing the parameters. And one particular model in these graphical models that is very useful for bioinformatics is the hidden Markov model, where we have this Markov chain of hidden states, and from each state we can obtain an observable. And this allows us to model things like, for example, in a family of sequences, we can observe the sequences, but we don't know which parts of the sequences are having the same kind of function, the same structure, the same part in whatever they have in common. So this we can delegate to the hidden variables, the hidden states. Those will represent these interesting properties, and the hidden Markov model will learn from the sequences that we presented. This can be done for organizing sequences of proteins in families, for identifying coding and non-coding regions in genes, and so on. We saw the forward algorithm for computing the probability of generating that sequence from that hidden Markov model, the Viterbi algorithm for computing the most likely sequence of hidden states from a sequence of observed states, and the Baum-Welch algorithm, which uses expectation maximization to train the hidden Markov model, giving a large set of examples. We can use this Baum-Welch algorithm to compute the values of the matrices for the transitions and for the emissions. This is a book I used in part for the Bayesian networks and the random Markov field examples. So if you want, you can take a look. But this falls outside the scope of the course. Is more particular for machine learning and has lots more information about this.